This is the story of Patagonia through deep time. Before there were mountains, before ice carved valleys, before even the idea of a horizon as we know it, there was time. Not time measured in hours or days, but time that moves like breath, almost imperceptibly. This is an invitation to listen on that timescale. As you settle in, imagine the land at the far southern edge of the world, Patagonia, not as a place on a map, but as a surface slowly discovering its own shape. Let the present moment soften. The sharp edges of today begin to blur. We are not in a hurry here. Nothing needs to happen quickly. Millions of years pass as gently as a passing thought. In this deep past, the land lies low and open. Rivers wander without urgency. Floodplains stretch wide beneath open skies. Sediment settles grain by grain, each layer a quiet memory placed upon the last. Far to the west, something stays. A distant margin tightens. The Earth's crust begins a long, patient conversation with itself, stretching, relaxing, then slowly drawing inward again. These movements are too slow to feel, but they will change everything. Basins form, sink, and fill. Stone gathers weight. Bones are buried, not in violence, but in stillness, resting in soft mud and sand, sealed away from time. Dinosaurs walk these plains, unaware they are becoming part of a story far larger than themselves. They drink from rivers that will someday vanish. They leave footprints that briefly hold their shape, then dissolve back into the landscape. Above and below, the planet works quietly. The surface records every motion, every rise, every collapse, every pause. This is not a story of sudden catastrophe. It is a story of accumulation, of pressure applied so slowly that stone learns to flow, of landscapes shaped not by moments, but by persistence. As the Andes begin their long ascent, the land responds. Basins bend under growing weight. Sediment thickens. Rivers shift their paths without protest. Nothing resists for long. And so, as we begin this journey, allow yourself to drift with the pace of the earth itself. Let the years stretch. Let distances widen. Let the idea of before and after dissolve. You are listening not to events, but to processes. Not to noise, but to motion so slow it feels like silence. This is Patagonia, not frozen in time, but endlessly becoming. This is the story of Patagonia through deep time. Long before ice shaped the poles, before grasslands spread across continents, before mountains cast long-range shadows across the land, Earth entered a chapter of its history defined not by cold, but by heat. This was the Cretaceous. If you could stand above the planet some 100 million years ago and look down, not as a human, but as a patient observer of deep time, the Earth would feel unfamiliar. The blues of the oceans would dominate your view, swelling outward across the continents. Coastlines would be drowned and reshaped. Inland seas would glitter where today there are plains, deserts, and cities. The planet would breathe warmth from equator to pole, its atmosphere thick with carbon dioxide, its oceans sluggish and heavy with heat. The Cretaceous was not a single moment, but a vast stretch of time, nearly 80 million years long, longer than any other period of the Phanerozoic eon. It began around 145 million years ago and ended abruptly at 66 million. But for most of its duration, Earth existed in a state that geologists now call a greenhouse world. There were no permanent ice caps, no frozen poles. Even at high latitudes, forests grew, rivers flowed, and dinosaurs walked beneath long summer suns and mild winter skies. The name Cretaceous comes from a quiet legacy this world left behind: chalk. Layer upon layer of microscopic carbonate shells, the remains of countless marine organisms, settled through warm seas and accumulated on ocean floors. Over millions of years, these soft oozes hardened into pale limestone. Today they stand exposed as cliffs and hillsides: the white cliffs of Dover, the chalk plains of Europe, the buried formations beneath North America. They are the fossilized memory of seas that once covered the land. But chalk is only the surface record. Beneath it lies a deeper story, written by fire and motion. During the Cretaceous, Earth's tectonic plates were restless. Across the globe, mid-ocean ridges swelled and lengthened as seaflow spreading accelerated. Hot, buoyant crust rose from the mantle, building vast underwater mountain chains that displaced seawater upward. Ocean basins grew shallower not because water increased, but because the seaflow itself was swollen with heat. The result was one of the highest global sea levels of the last half-billion years, up to 200 meters higher than today. The continents responded by drowning. Shallow seas flooded continental interiors, transforming landmasses into archipelagos and low-lying plains. In North America, a narrow connection between the Arctic and the tropics opened into a vast inland sea. The western interior seaway stretched nearly 3,000 miles, from what is now the Gulf of Mexico to the Arctic Ocean, splitting the continent into eastern and western halves. Where today there are wheat fields and prairies, there were once warm, shallow waters rolling gently over carbonate platforms and muddy shelves. Marine reptiles cruised above submerged plains. Plankton bloomed in sunlit waters. Fine sediments settled slowly to the seafloor, building the rock layers that would one day record this vanished ocean. Elsewhere, the Cretaceous Sea dominated the equatorial world. It was a broad, warm seaway separating northern continents from southern Gondwana, its margins lined with reefs and carbonate platforms built not by corals alone, but by strange reef builders now long extinct, rudest bivalves, whose massive shells formed the backbone of tropical shallow seas. The climate that sustained this flooded world was unlike anything modern Earth has known. Global temperatures were high, but more importantly, they were even. Heat flowed efficiently from equator to pole through warm oceans and a dense atmosphere. Deep waters, which today hover just above freezing, reached temperatures of 15 to 20 degrees Celsius. Polar regions remained ice-free, bathed in seasonal light but spared seasonal cold. Evidence of this warmth lies frozen in stone. Dinosaur fossils have been found within 15 degrees of the ancient South Pole. Animals adapted not to darkness and cold, but to mild conditions and lush vegetation. Plants that today would never survive polar winters flourished at high latitudes, their remains scattered through sediments that once lay far from the equator. Yet this warm world was not calm. Beneath the continents and oceans, Earth's mantle pulsed with energy. In several places, enormous upwellings of hot rock rose toward the surface, breaking through the crust in events that dwarfed any volcanic eruptions seen in human history. These were the large igneous provinces, the Ontong Java Plateau, the Kerguelen Plateau, the High Arctic Province, and others. each formed by massive outpourings of basalt over geologically short periods of time. When these provinces erupted, they released not only lava, but vast quantities of carbon dioxide, sulfur gases, and metals into the atmosphere and oceans. The effects were global. The climate warmed further. Rainfall intensified. Nutrients washed from continents into the sea. And slowly, silently, the oceans began to lose their breath. Throughout the Cretaceous, intervals occurred when large portions of the world's oceans became depleted in oxygen. These events, known as oceanic anoxic events, were not moments of instant catastrophe, but prolonged episodes lasting hundreds of thousands of years. In stagnant, stratified waters, organic matter accumulated faster than it could decay. Oxygen vanished from the depths. Life retreated upward, or died. Black shales formed on the seafloor, rich in organic carbon, recording times when the normal rhythms of ocean circulation failed. These layers would later become key archives for geologists, preserving chemical signatures of ancient crises and recoveries. While the oceans struggled, the continents themselves were being reshaped by collision. Along the western margin of North America, oceanic plates converged relentlessly with the continent. Subduction drove mountain building on a continental scale. The Sevii and later Laramide orogenies folded and thrust rock layers eastward, lifting early versions of the Rocky Mountains and loading the crust beneath them. As mountains rose, adjacent regions bent downward under their weight. Fallen basins formed, long, subsiding troughs that filled with sediment eroded from the growing ranges. Rivers carried sand and mud eastward into shallow seas, where they mingled with marine sediments and volcanic ash. These basins were not just geological features. They were landscapes, dynamic, shifting environments of rivers, floodplains, deltas, and coastal wetlands. They were places where dinosaurs lived, moved, fed, and died, their bones buried and preserved by the same processes that shaped the land. By the middle of the Cretaceous, all of these forces, high sea levels, extreme warmth, vigorous tectonics, and widespread volcanism, were converging toward a peak. The world was approaching its most intense greenhouse state. Around 100 million years ago, during the interval geologists call the Cenomanian, Earth crossed a threshold. Sea levels rose to near their maximum. Ocean temperatures climbed. Continental interiors flooded further. Plate motions reorganized across the globe, altering the geometry of spreading ridges and subduction zones. What followed was one of the most profound disruptions of the global carbon cycle in Earth's history. At the boundary between the Cenomanian and the Turonian ages, the oceans entered a crisis so extensive that it left a fingerprint detectable on every continent. Carbon isotopes shifted abruptly, signaling massive burial of organic matter. Black shales spread across ocean basins from the Proto-Atlantic to the Cretaceous, from North Africa to the heart of North America's inland sea. This was oceanic anoxic event too. But to understand how the oceans suffocated, and how life on land continued to flourish even as the seas struggled, we must move closer. We must descend from the planetary scale to the level of basins and currents, coastlines and floodplains. We must enter the flooded heart of a continent. In the next part of this story, we will travel into the western interior seaway at the height of the Cenomanian supergreenhouse, a shallow ocean stretching from pole to tropics, its waters warm, productive, and increasingly unstable. There, in sediments and chemistry, we will watch the oceans change and see how the forces deep within the Earth reshaped life above. By the time the Cenomanian age fully unfolded, Earth had crossed into a state few worlds ever experience. This was not merely a warm planet. It was a super greenhouse, a world in which heat was abundant, oceans were swollen, and the boundaries between land and sea had largely dissolved. The continents no longer stood as isolated landmasses bordered by narrow coasts. Instead, they were low, broad platforms, flooded from their margins inward, their interiors reshaped into vast, shallow seas. Sea level stood near its maximum for the entire Cretaceous. In many reconstructions, it was higher than at any point in the last 500 million years. The result was a geography dominated by water, epicontinental seas that covered millions of square kilometers, rarely deeper than a few hundred meters, but stretching farther inland than any modern ocean ever has. Nowhere was this transformation more dramatic than in North America. What had once been a continuous continent was split in two by water. From the Arctic Ocean in the north to the warm waters of the Gulf region in the south, a shallow sea flooded the continental interior. The Western Interior Seaway extended nearly 6,000 kilometers in length and, at its widest, approached 2,000 kilometers across. This was not a narrow channel or a temporary incursion. It was a persistent oceanic feature, shallow but immense, with gently sloping margins and a low-relief seafloor. At its deepest points, it reached perhaps 500 meters, but much of it was far shallower, sunlit, productive, and warm. Along its eastern and western shores, coastal plains formed broad belts of wetlands, deltas, and lagoons. Rivers drained from rising mountain belts to the west and from older uplands to the east, delivering sediment, nutrients, and fresh water into the seaway. These inputs fueled extraordinary biological productivity. Surface waters bloomed with plankton. Microscopic algae flourished, forming the base of a food web that supported fish, ammonites, marine reptiles, and seabirds. Carbonate muds and fine clays settled from the water column, accumulating layer upon layer on the seafloor. But beneath the surface, the system was becoming unstable. The warmth that defined the Cenomanian world had consequences. Warm water is less dense than cold, and as surface waters heated further, the oceans became increasingly stratified. Mixing between surface and deep layers weakened. Oxygen, replenished at the surface through contact with the atmosphere, struggled to reach the depths. At the same time, intensified rainfall and runoff, products of a strengthened hydrologic cycle, washed enormous quantities of nutrients from the continents into the sea. Rivers carried phosphorus, iron, and other elements liberated by chemical weathering under hot, humid conditions. Volcanic ash from distant eruptions added further pulses of nutrients. Productivity soared. Plankton multiplied rapidly in surface waters, drawing carbon dioxide from the atmosphere and converting it into organic matter. When these organisms died, their remains sank toward the seafloor. Under normal conditions, much of this material would be recycled, consumed by bacteria, decomposed, and returned to the water as dissolved nutrients. But the Cenomanian oceans were no longer normal. As organic matter accumulated faster than it could decay, oxygen was consumed in the process. Bottom waters became depleted, first locally, then across broad regions. In places, oxygen vanished entirely. Anoxia crept across the seafloor. In the Western Interior Seaway, this process left a clear signature. Geological sections record repeated intervals where oxygen-poor conditions coincided with key stage boundaries, including the transition from the Cenomanian into the Turonian. These were times when circulation was restricted, sea level was high, and productivity was intense. Water mass studies reveal a complex and shifting system. At different times, the seaway received influences from the north, cooler, boreal waters flowing southward, and from the south, where warmer Tethyan waters entered from equatorial regions. Locally sourced waters, enriched by river input, laid atop these larger currents. Near the Cenomanian-Turonian boundary, a major reorganization occurred. Sea level reached its peak transgression, fully connecting the seaway to northern boreal waters. Circulation patterns shifted, altering temperature gradients and oxygen distribution throughout the basin. These changes were not isolated to North America. Across the globe, similar processes were unfolding. The Proto-North Atlantic, still narrow and young, accumulated thick sequences of organic-rich black shales. Along the margins of the Cretaceous Sea, carbonate platforms gave way to deeper, oxygen-poor environments. North African shelves recorded widespread anoxia. In basin after basin, the same story appeared: warm waters, high productivity, oxygen loss. At the heart of this transformation lay volcanism. During the Cenomanian and early Turonian, Earth experienced one of the most vigorous episodes of large igneous province activity in its history. Massive volcanic plateaus were forming or continuing to erupt. Kerguelen in the southern oceans, Ontong Java in the Pacific, the Caribbean Plateau, the High Arctic Province, and others. These were not single eruptions, but sustained volcanic episodes lasting hundreds of thousands to millions of years. Each pulse injected enormous quantities of carbon dioxide into the atmosphere, reinforcing greenhouse conditions. Sulfur gases and trace metals entered the oceans, altering chemistry and nutrient cycles. Recent research has linked oceanic anoxic event too directly to these volcanic pulses, particularly those associated with the Kerguelen Plateau. As volcanism intensified, the global carbon cycle was pushed out of balance. Carbon isotopes shifted sharply, recording a massive increase in the burial of organic carbon in marine sediments. This burial acted as both symptom and partial remedy. As organic matter accumulated on oxygen-starved seafloors, carbon was locked away in black shales. Over time, this drawdown of atmospheric carbon dioxide may have helped stabilize climate, but not before profound disruptions had occurred. Marine ecosystems were reshaped. Some organisms thrived in nutrient-rich surface waters. Others, dependent on oxygenated bottoms, vanished from large regions. Opportunistic species, those tolerant of stress, spread widely. Planktonic foraminifera such as Heterohelix increased in abundance, their shells now used by geologists as markers of anoxic intervals. Trace metals tell the same story. Chromium, copper, cobalt, osmium, and neodymium isotopes shifted in concert, pointing to intensified submarine volcanism and altered ocean circulation. Manganese was stripped from sediments under low oxygen conditions. Phosphorus cycled in feedback loops that further amplified productivity and anoxia. And yet, even as the oceans struggled, the land told a different story. Along the margins of the western interior seaway, broad coastal plains supported forests, wetlands, and river systems. Dinosaurs moved through these landscapes in great numbers. Herbivores browsed on abundant vegetation. Predators followed, Trackways crisscrossed mudflats and floodplains, recording migrations along the shifting shores of the sea. Far to the south, in what is now Patagonia, similar processes were at work, but expressed through a different landscape. There, the western margin of Gondwana was alive with tectonic motion. Subduction along the Proto-Andean margin drove uplift to the west and subsidence to the east. Foreland basins formed, broad and low-lying, filled with braided rivers and floodplains that stretched for hundreds of kilometers. These basins were warm, humid, and green, nothing like the cold, windswept Patagonia of today. Rivers wandered across sandy plains. Overbank silts accumulated during seasonal floods. Vegetation flourished, fed by runoff from rising highlands and nourished by volcanic ash. It was in these environments, during the Cenomanian and early Turonian, that some of the largest animals ever to walk the earth lived. Titanosaurs, giant sauropod dinosaurs, moved through these floodplains in herds. Their immense bodies required constant access to food, and the productivity of these tectonically active basins made such size possible. The same processes that drove anoxia in the oceans, warm climate, high vigorous weathering, also fueled plant growth on land. The Cenomanian supergreenhouse was thus a world of contrasts. The seas were warm, shallow, and in places suffocating. The continents were flooded but fertile. Tectonic forces created both crisis and opportunity, reshaping habitats on land even as they destabilized marine systems. Eventually, the forces driving anoxia began to wane. Volcanic inputs declined. Circulation patterns shifted. Sea level stabilized and then slowly fell. By the early Turonian, oxygen returned to many basins, and black shale deposition diminished. But the world that emerged was not a return to balance as we know it. Sea levels remained high. Temperatures stayed warm. Chalk once again dominated marine sedimentation, recording more stable conditions above former anoxic layers. The greenhouse world persisted, carrying life forward toward the later chapters of the Cretaceous. And on land, giants continued to walk. In the next part of this story, we will follow the tectonic forces beneath their feet, tracking the global plate reorganization that drove these extremes and then narrowing our focus to the southern continents. There, in the foreland basins of Patagonia, we will meet Argentinosaurus and step into the daily life of a dinosaur shaped by a planet in motion. Beneath the warm seas and fertile floodplains of the Cenomanian world, the Earth itself was changing direction. Tectonic plates, vast slabs of lithosphere drifting atop the mantle, do not always move in steady, predictable paths. At certain moments in deep time, the forces that drive them reorganize. Directions shift. Boundaries adjust. New stresses propagate across the globe. The mid-Cretaceous was one of those moments. Around 100 to 105 million years ago, geologists detect a subtle but global signal recorded on the ocean floor. Fracture zones bend. Spreading ridges realign. Magnetic stripes trace changes in motion across thousands of kilometers. This episode, sometimes called the 100 million year event, marks a worldwide reorganization of plate tectonics. In the Indian and Pacific Oceans, spreading centers changed orientation. The Pacific plate itself altered its direction of motion, leaving a kinked record etched into the seafloor. In the Wharton Basin and adjacent regions, fracture zones reveal abrupt shifts that could only have occurred if the forces acting on the plates had changed. These changes did not happen in isolation. Along the margins of eastern Gondwana, what would become Australia, Antarctica, and parts of Southeast Asia, subduction systems stalled, rolled back, or shut down entirely. Slabs that had once pulled plates steadily toward trenches detached or weakened. The balance of forces that had guided plate motions for tens of millions of years was disturbed. As resistance changed in some regions, plates accelerated in others. Mid-Cretaceous seafloor spreading rates increased across much of the globe. New oceanic crust was produced rapidly, and because young crust is hot and buoyant, it stood higher than older seafloor. Ocean basins grew shallower, displacing seawater onto the continents. This tectonic swelling of the oceans was a major driver of the extreme sea level high stands seen during the Cenomanian and early Turonian. At the same time, the mantle responded. Large mantle plumes, columns of hot rock rising from deep within the earth, became unusually active. Some had been present earlier, but during the mid-Cretaceous they reached a peak in productivity. Their arrival at the base of the lithosphere triggered massive outpourings of basalt, forming the large igneous provinces that scar the geological record. These provinces were not random. Their timing and distribution suggest a deep connection between plate reorganization and mantle dynamics. As subduction patterns shifted and plates changed speed, stresses within the mantle adjusted. Upwellings intensified. Magma found new pathways to the surface. The result was a planet releasing heat and gas on a colossal scale. Nowhere were the consequences more evident than along the western margins of the Americas. In North America, the Farallon and Kula oceanic plates plunged beneath the continent in a long-lived Andean-style subduction system. Compression built mountain belts along the Cordillera, folding and thrusting sedimentary layers eastward. The severe orogeny dominated this phase, thin-skinned deformation that stacked sheets of rock like pages in a book. The growing mountain belt weighed down the crust ahead of it. To the east, the fall bent and subsided, creating accommodation space for the western interior seaway. Marine waters flooded inland, filling the tectonically generated basin with muds, carbonates, and volcanic ash. This was not a passive sea. It was a direct product of plate convergence. Volcanic arcs along the margins supplied ash that settled as bentonite layers, thin, distinctive horizons that now serve as time markers for geologists. Clastic wedges advanced eastward during pulses of uplift. Each thrust event left its imprint in the stratigraphic record. Farther south, along the margin of Gondwana, similar forces were shaping a different landscape. Patagonia lay on the southwestern edge of the supercontinent, above a long-lived subduction zone where oceanic crust descended beneath South America. During the early Cretaceous, this region experienced back-arc extension. Basins opened behind the volcanic arc as the crust stretched and thinned, forming rifted lowlands and shallow marine embayments. But by the mid-Cretaceous, the tectonic regime began to change. Extension gave way to compression. Subduction intensified. The earliest phases of Andean mountain building began to assert themselves. Back-arc basins such as Rocas Verdes started to close and invert. Their sediments folded and uplifted as convergence increased. This shift transformed Patagonia's geography. To the west, Proto-Andean ranges rose gradually, not yet the towering Andes of today, but elevated enough to influence drainage and climate. To the east, fallen basins formed in response, subsiding under the growing load of the mountains. These basins became vast, low-relief landscapes crossed by rivers and dotted with floodplains. Volcanism accompanied this transition. Thick volcanic successions accumulated in the Patagonian magmatic belt. Granitic intrusions crystallized at depth as the arc migrated. Ash fell repeatedly across the basins, enriching soils and adding layers to the sedimentary record. The land was alive with motion. Rivers shifted course as basins subsided. Channels braided and rebraided across sandy plains. Seasonal floods spread fine silts over wide areas, building levees and overbank deposits. Lakes formed in low spots, then filled and vanished as sediment accumulated. These were ideal conditions for preservation. Animals that died on floodplains were rapidly buried. Bones accumulated in channel lags. Trackways hardened in drying mud. Over millions of years, tectonic subsidence protected these deposits from erosion, sealing a record of life within the rock. And life took full advantage. The warm, humid climate of the Cenomanian and early Turonian, combined with tectonically enhanced nutrient supply, supported dense vegetation. Forests lined rivers. Ferns and conifers dominated floodplains, joined increasingly by early flowering plants. Primary productivity was high and sustained. For herbivores, this was a world of abundance. Titanosaurs, among them Argentinosaurus, grew to extraordinary sizes, their mass supported by continuous access to food and stable environmental conditions. Herds moved across floodplains, following river corridors that shifted slowly through time. Their migrations were shaped not by mountains or deserts, but by the subtle gradients of subsiding basins. Predators followed. Giant theropods such as Giganotosaurus and Maposaurus occupied the same regions, their presence recorded in bone beds that hint at repeated use of hunting grounds or even group behavior. All of this unfolded against a backdrop of global change. While Patagonia's basins filled with life, the oceans continued to respond to tectonic and volcanic forcing. Oceanic anoxic event 2 reached its peak, then slowly declined as volcanic inputs waned and circulation patterns adjusted. Chalk once again accumulated over former black shales, marking a partial recovery. But the tectonic engines did not stop. As the Proto-Andes continued to rise, the foreland basin kept subsiding. Sediment piled atop sediment, burying floodplains deeper with each passing cycle. Unlike regions later eroded or uplifted too rapidly, Patagonia's basins preserved their stories intact. Above the dinosaurs, the sky told its own story. The atmosphere was heavy with warmth. Storms built quickly, fueled by heat and moisture. Rain fell in intense bursts, feeding rivers and renewing soils. There were no freezing winters, no prolonged droughts, just variation within an overall humid, productive regime. This climate, too, was a product of tectonics. Volcanic gases sustained high atmospheric CO. Mountain building influenced rainfall patterns without yet creating a strong rain shadow. The land remained open, green, and interconnected, a continuous habitat for giants. For millions of years, this balance held. Argentinosaurus lived its life not as an anomaly, but as a natural outcome of a world tuned toward size. Warmth reduced metabolic constraints. Productivity supported massive herbivory. Low relief and broad floodplains allowed movement without barriers. The giants were not fighting the planet. They were expressions of it. Yet even as they thrived, the deeper forces that shaped their world continued to shift. Mountains would rise higher. Climates would change. Rivers would be redirected. The stability that allowed such giants to exist was not permanent. Even as the age of giants stretched on, the southern edge of the world grew restless. Far to the south of the great Patagonian floodplains, between what are now 46 and 52 degrees south latitude, the Earth opened again. Along the Andean margin, a discontinuous chain of volcanoes rose and fell, forming a broken arc that traced the slow collision of oceanic plates with the continent. This was not a single volcanic belt, but a system, fragmented, uneven, and changing with time. To the north, between 46 and 49 degrees south, the southern Andean arc burned most brightly. Andesitic stratovolcanoes and viscous dacitic domes punctuated the skyline of what is now Santa Cruz province. These volcanoes were fed by subduction beneath the continent, by oceanic crust descending, melting, and returning to the surface as fire. Farther south still, the nature of volcanism changed. In the region that would become the Fuegian Andes, between 50 and 52 degrees south, volcanic rocks tell a different story. Here, mafic lavas erupted in a retroarc setting, remnants of an older world, when seaflow spreading had once opened the Rocas Verdes basin. By the late Cretaceous, that basin was closing, its oceanic crust compressed, uplifted, and slowly destroyed. Volcanic activity waned southward as back-arc closure dominated. Fire gave way to deformation. Basins folded. Landscapes tightened and rose. For dinosaurs living in Patagonia, these volcanic belts were not distant abstractions. They were active, disruptive neighbors. Eruptions were episodic, not constant, but when they came, they reshaped life on the ground. Ash fell across floodplains in thick, choking sheets. Vegetation was smothered. Ferns collapsed beneath weight they could not bear. Rivers carried gray slurry downstream, clogging channels and burying soils beneath sterile layers of fine volcanic dust. For herbivores like titanosaurs, these events meant movement. Herds were forced to abandon familiar feeding grounds, traveling long distances in search of untainted vegetation. Migration routes stretched farther. Seasonal movements became more urgent. The immense size that once offered security now demanded even greater landscapes to sustain it. For predators, the effects were subtler but no less real. Fine ash particles lingered in the air, irritating lungs and eyes. Large theropods, animals dependent on stamina, vision, and coordination, likely found hunting more difficult during eruption pulses. Reduced efficiency meant missed kills, longer pursuits, and higher energetic costs. Yet these disruptions were not endings. Volcanism destroyed, but it also renewed. In the months and years following eruptions, ash-enriched soils sparked explosive plant growth. Ferns were often the first to return, carpeting floodplains in dense green mats. Flowering plants followed quickly, taking advantage of disturbed ground. In some cases, post-eruption landscapes supported brief population booms, as fresh vegetation spread faster than herbivores could consume it. Life adapted, as it always had. By the late Cretaceous, Patagonia's dinosaur communities had changed, but they had not diminished. Some giants were gone. Carcharodontosaurid predators, once dominant, faded from the record earlier than others. In their place, new survivors rose. Titanosaurs endured. Not all remained colossal. In a world of shrinking habitats and increasing topographic complexity, smaller-bodied saltosaurines thrived. Forms like Saltosaurus and Nuquensaurus, some armored, some compact, persisted into the very latest Cretaceous. Southern refugia offered stability when northern regions became more fragmented. Predators adapted as well. Abelisaurids, stocky, powerful theropods with reduced forelimbs and reinforced skulls, proved remarkably resilient. Species like Carnotaurus and Orcosaurus ranged widely across Neuquén and Rio Negro provinces, thriving until just a few million years before the end. Alongside them, Megaraptorans and Unenlagians, sleeker, more agile hunters, occupied specialized niches. In southern Patagonia and Chile, forms like Ostroraptor survived nearly to the final chapter of the dinosaur era. Volcanism, tectonics, and climate shifts stressed these animals, but they did not defeat them. Extinction, when it came, arrived from the sky. After the dinosaurs vanished, Patagonia did not become what it is today overnight. The transformation took tens of millions of years. As the Cretaceous gave way to the Cenozoic, greenhouse warmth gradually yielded to cooling. Sea levels fell. Epicontinental seas withdrew. The Andes rose higher, first 2 kilometers, then 3, then more than 4, until they became a true continental barrier. Rain shadows intensified. Moist westerly winds dumped their water on the rising mountains, leaving the eastern plains increasingly dry. Subtropical forests retreated. Grasslands and open steppes spread eastward. Rivers cut deeper into uplifted rock, exposing the very dinosaur beds once buried and protected by subsidence. Ice eventually followed. By the late Neogen and Pleistocene, glacier carved valleys and fjords into the Andes. The Patagonian ice sheet advanced and retreated, reshaping the land yet again. The warm, river-laced world of Argentinosaurus became unrecognizable. New giants took the dinosaurs' place, mammals this time. Ground sloths, glyptodonts, and other megafauna roamed the plains, only to vanish much later, in the shadow of human arrival. Today, Patagonia stands as a land of contrast. Granite towers like Fitzroy and Torres del Paine rise sharply against the sky. Eastern plains stretch wide and windswept, home to guanacos and saline lakes. Fierce westerlies roar year-round. Glacier carved dramatically into turquoise waters, some advancing briefly, many retreating fast. It is a landscape still in motion. And beneath it all, the older worlds endure, locked in stone, waiting to be read. In the final part of this story, we will follow Argentinosaurus through the lens of time, examining how its world began to change, how ecosystems responded, and how a planet that once favored giants slowly moved toward a very different future. For most of its existence, the world of Argentinosaurus felt timeless. Generations rose and fell beneath the same warm skies. Rivers shifted their courses, but never vanished. Forests advanced and retreated across floodplains, yet food remained plentiful. The giants grew, migrated, nested, and died in landscapes shaped by forces so slow they seemed eternal. But Earth does not stand still. Even during the height of the super greenhouse, the processes that had pushed the planet to its extremes were already beginning to change. Volcanic pulses waxed and waned. Ocean circulation adjusted. Tectonic stresses redistributed themselves once more. These shifts were subtle on the scale of a lifetime, but profound across deep time. In the oceans, the most dramatic crisis of the mid-Cretaceous, Oceanic Anoxic Event 2, was drawing toward its end. The burial of vast amounts of organic carbon in black shales had altered the balance of the global carbon cycle. Slowly, atmospheric carbon dioxide levels began to stabilize. Circulation strengthened in some basins, allowing oxygen to return to previously suffocating depths. Chalk replaced black shale once again, recording a partial recovery of marine conditions. This recovery was uneven. Some regions reoxygenated quickly, others remained stressed for longer. But the peak of global anoxia passed, leaving behind a transformed ocean ecosystem, one that would persist through the rest of the Cretaceous. On land, the changes were quieter. Sea levels remained high into the early Turonian, and the great epicontinental seas still flooded continental interiors. The western interior seaway continued to divide North America. Patagonia's foreland basins remained broad and low-lying. Warm temperatures persisted, and ice remained absent from the poles. For dinosaurs, there was no sudden collapse, no mass die-off, no clear signal of crisis. Instead, life continued, adaptive, resilient, and regionally diverse. High sea levels and fragmented continents encouraged provinciality. Dinosaur faunas became increasingly distinct from one region to another, shaped by seaways, uplifts, and intermittent land connections. Europe, broken into islands, hosted smaller, sometimes dwarfed species. North America's eastern and western halves developed different lineages. Southern Gondwana followed its own evolutionary paths. In Patagonia, titanosaurs remained dominant herbivores. But even among giants, diversity increased. Different forms specialized in different feeding strategies, body proportions, and growth patterns, allowing multiple massive species to coexist in the same broad regions. Predators diversified as well. Large carcharodontosaurids continued to rule as apex hunters, while smaller theropods filled more specialized ecological roles. Feathered dinosaurs, relatives of birds, were present, exploiting niches that giants could not. The ecosystems were complex, layered, and stable, yet always contingent on the environment beneath them. Tectonics continued to reshape the land. Along the western margin of South America, compressions slowly intensified. The Proto-Andes rose incrementally higher, beginning to influence rainfall patterns more strongly. Drainage networks adjusted. Some rivers were redirected. Foreland basins deepened in places and filled in others. These changes did not erase habitats, but they altered them. Floodplains shifted position. Migration routes changed subtly over thousands of years. Herds followed vegetation as it tracked moisture and soil fertility. The dinosaurs adapted, not consciously, but through movement, behavior, and slow evolutionary response. Yet the conditions that favored extreme gigantism were not permanent. Over tens of millions of years, the global climate would begin to cool. Sea levels would fall from their mid-Cretaceous peaks. Mountain belts would rise higher, fragmenting lowland corridors. Rain shadows would intensify. The open, uniformly productive landscapes that once stretched across continents would become more compartmentalized. For Argentinosaurus, the window of opportunity was narrow in geological terms. It lived at the crest of a wave, where warmth, productivity, tectonic stability, and geography aligned just long enough to allow bodies of unprecedented size to evolve and persist. Before that crest, the world was still assembling. After it, the world would slowly close. And yet, extinction did not come swiftly. Titanosaurs remained successful through much of the late Cretaceous. They adapted to new environments, sometimes becoming smaller, sometimes armored, sometimes changing their growth strategies. The lineage endured until the very end, until a moment entirely unrelated to plate tectonics or climate trends intervened. A moment recorded not in slow sedimentation, but in a thin layer of clay. But that end should not overshadow what came before. For millions of years, Earth sustained a world unlike any that exists today, a world of warm poles and flooded continents, of restless plates and breathing oceans, of rivers that wandered endlessly across green plains. Argentinosaurus did not merely survive in that world. It was shaped by it. Its immense size was not excess. It was equilibrium, a living expression of a planet in balance with heat, motion, and time. And long after the giants were gone, the rocks remained. Chalk cliffs rising from ancient seas. Black shales marking oceans without breath. Sandstones preserving footprints pressed into soft floodplain mud. Each layer a sentence in a story written by a moving earth. That story reminds us that worlds are not static. They are built, sustained, and transformed by forces far larger than any single species. And for a brief, remarkable interval in Earth's history, those forces made room for giants. Today, Patagonia feels immense in a different way. The wind moves constantly across open steppe. Snow-fed rivers cut through dry plains. To the west, the Andes rise high enough to split clouds, wringing moisture from the air and casting long-range shadows across the land. It is a place defined by distance, cold, and exposure. But beneath the surface, the older world remains. The rocks of Patagonia still carry the memory of warmth. Sandstones laid down by braided rivers remember floods that spread across green plains. Fine silts preserve the quiet moments between storms. Volcanic ash marks distant eruptions that once fertilized forests and floodplains. And in some of those rocks, bones still lie. They tell us that this land was once gentle enough, fertile enough, and stable enough to support the largest animals ever to walk on Earth. Not through chance, but through alignment of climate, tectonics, oceans, and time. That alignment did not last. As plates continued to converge, the Andes rose higher. Winds shifted. Rainfall patterns changed. Rivers were redirected. The open, low-relief world of the Cretaceous slowly gave way to a fragmented landscape, then to the cold, arid Patagonia we recognize today. Later still, glacier-carved valleys and fjords, sealing the transformation. What ended the age of dinosaurs, however, was not this slow change. It was sudden, violent, extraterrestrial. Yet the deeper lesson of the Cretaceous lies not in its ending, but in its long stability before that moment. For tens of millions of years, Earth existed in a state far warmer than today, with higher sea levels, ice-free poles, and a climate driven by elevated carbon dioxide. Life adapted. Ecosystems flourished. Entire worlds emerged that now feel alien to us. We live on a different Earth, but not a disconnected one. The same processes that shaped the Cretaceous still operate beneath our feet. Plates still move. Volcanoes still breathe carbon into the atmosphere. Oceans still circulate heat around the globe. Climate still responds, sometimes slowly, sometimes abruptly. The rocks remind us that Earth is capable of sustaining worlds very different from the one we know, and that such worlds can persist far longer than human history has existed. When we study Argentinosaurus, we are not just marveling at size. We are looking at a moment when the planet itself made room for giants. Understanding that world does not tell us what will happen next, but it tells us what is possible when deep forces align, when climate shifts, and when life responds not with fragility, but with transformation. The giants are gone, the Earth remains, and it is still writing its story. Imagine Patagonia not as it is today, but as a land still finding its shape. In the deep past, during the final chapters of the age of dinosaurs, this southern world lay low and open, a vast mosaic of rivers, floodplains, shallow lakes, and distant volcanic arcs. Beneath its surface, the Earth was already restless. Invisible forces were beginning a long conversation between stone, fire, and time, one that would continue for tens of millions of years. The Neuquén Basin, now famous for its dinosaurs, was born as a back-arc basin during the Jurassic. It expanded and sagged under extension, then tightened again as compression returned. Over and over, the crust breathed in and out. Each cycle created space for rivers to wander, for sediments to pile up, for bones to be buried gently and preserved in silence. As the late Cretaceous gave way to the Cenozoic, the tone of the Earth's movements changed. Extension faded. Compression took over. To the west, the Andean margin awakened fully. Fold-and thrust belts advanced eastward like slow, deliberate waves. Older rocks were stacked atop younger ones. Basins tilted. Deposition migrated, step by step, farther into the foreland. Patagonia, once broad and low, began to wrinkle and rise. Foreland basins formed under the growing weight of the Andes, great sediment traps like the Mogollons Basin in the south and the evolving Neuquén system in the north. Rivers carried enormous loads of sand and mud eastward, burying landscapes again and again. In some places, sediment accumulated kilometers thick, pressing fossils into stone while preserving astonishing detail, bone textures, growth rings, even traces of feeding. Yet this growth was never simple. Through the Cenozoic, Patagonia became a broken foreland. Instead of one smooth basin, the crust fractured into blocks. Basement chord uplifts rose quietly, while neighboring basins sank. The land became segmented, highs and lows arranged like slow waves frozen in rock. Ancient rift faults, inherited from much earlier times, guided where the Earth would bend and break again. Above it all, the Andes continued to rise. Subduction beneath South America shifted in character. Sometimes the slab dipped steeply, at other times it flattened, transmitting stress far inland. Flat slab episodes helped fracture the foreland even more, lifting blocks hundreds of kilometers from the trench. Later, ridge subduction opened slab windows, allowing warm mantle to rise and gently buoy the surface upward. These deep processes lifted plateaus, warped rivers, and subtly tilted entire regions. By the Neogen, Patagonia was no longer a quiet sedimentary lowland. It was a landscape in motion. Then came the ice. Around 6 million years ago, alpine glacier began to occupy valleys that had once carried only rivers. The change was dramatic. Erosion rates surged, doubling, tripling, sometimes increasing more than tenfold. Valleys that had deepened slowly for millions of years were suddenly carved with astonishing speed. Ice thickened and flowed along structural weaknesses, grinding valleys into broad U-shapes. Tributaries were left hanging. Basins were carved far below sea level, later filling with lakes or fjords. For a brief geological moment, Patagonia was reshaped faster than almost anywhere on Earth. But even this fury did not last forever. After about 3 million years, erosion began to slow. The landscape adjusted. Valleys widened rather than deepened. The mountains approached a new balance, one where uplift and erosion spoke more quietly to each other. Yet the marks of that early glacial pulse remain everywhere: deep fjords, oversteepened walls, and lakes cradled in stone. Today, the Andes still rise. Post-glacial rebound gently lifts valleys freed from ice. Mantle flow and slab dynamics continue to warp the surface. Rivers still carry the memory of uplift, flowing eastward across broken forelands toward the Atlantic, while short, steep catchments drain west into Pacific fjords. Patagonia, as we see it now, is not finished. It is a living archive of subduction and sediment, of burial and exposure, of ice and fire, of patience measured not in years, but in millions of them. The dinosaurs are gone, but the basins that once held them still shape the land. The glacier retreat, but their scars guide every river. And beneath it all, deep beneath the silence of wind and stone, the earth is still moving, slowly, steadily, dreaming its next landscape into being. In the long age before mountains dominated the horizon, Patagonia was a land that lay open to the sky. The ground was low and broad, stretching outward rather than upward. Rivers moved slowly across wide floodplains, changing course without urgency, dividing and rejoining like wandering thoughts. Shallow lakes formed and faded. Seasonal wetlands breathed in and out with the climate. This was the world of the Neuquén Basin. It existed not as a single place, but as a process, a surface shaped by subsidence, where the earth gently sagged under its own weight, creating room for water, sediment, and life. Grain by grain, sand and mud settled into this space. Each flood laid down another thin layer. Each dry season allowed the surface to rest. Dinosaurs moved through this landscape not as rulers, but as participants. They followed river corridors. They crossed floodplains under open skies. Their lives were woven into the rhythm of water and sediment. When they died, their bodies were not always torn apart or scattered. Often, they were covered quietly, by a bank collapse, by a rising flood, by windblown sand. Burial was gentle. Over time, pressure increased. Water moved through pores in the sediment. Minerals began to replace organic matter, slowly, patiently. Bone turned to stone without losing its shape. Growth lines, textures, even traces of feeding remained locked in place. Above this quiet preservation, the earth continued its deeper motions. The basin did not remain still. It subsided, paused, and subsided again, each movement opening new space, each pause allowing rivers to reorganize themselves. These cycles repeated for millions of years. The landscape learned how to remember. Far to the west, beyond the floodplains and wetlands, the margin of the continent was changing. What had once stretched began to draw inward. The tectonic regime shifted slowly, almost imperceptibly. Back arc extension gave way to compression. The Earth's crust, once relaxed, began to shorten and thicken. This was the beginning of the Andes. Not as mountains yet, but as pressure. Fold and thrust belts started to form along the western edge of Patagonia. Rocks were pushed atop other rocks, layers stacked like pages being gently pressed together. The weight of this growing orogen was felt far from its source. The Neuquén Basin responded by bending. As the Andes rose, even slightly, the crust east of them flexed downward. New accommodation space opened. Sediment flowed in to fill it. Deposition shifted eastward, step by step, as older basin areas were uplifted and incorporated into the growing mountain front. What had once been active lowlands became part of the rising edge of the continent. Rivers adapted. Channels migrated. Floodplains narrowed or expanded. Sediment loads increased as erosion intensified in the west. Still, the pace remained slow. There were no sudden cliffs, no dramatic peaks. Only a gradual tightening of the Earth's surface, felt over millions of years. Stone began to carry more weight than before. As the Andes continued their long ascent, Patagonia entered a new phase. The foreland basin system expanded. Under the increasing load of the mountains, the crust flexed like a great, slow bow. Large retroarc basins formed, trapping vast quantities of sediment eroded from the rising Andes. But this foreland was not smooth or simple. Over time, it began to break. Deep within the crust, ancient faults, remnants of much older rifting, were reactivated. Blocks of basement rock rose quietly while neighboring regions subsided. The once continuous basin became fragmented. This is what geologists call a broken foreland. But from the surface, it appeared as subtle change. A low uplift here, a shallow basin there. Rivers adjusted their gradients. Sediment pooled in new depressions. The land became segmented, not violently, but persistently. Each uplift altered drainage. Each basin collected its own sedimentary story. Some areas preserved thick successions of fluvial deposits. Others were slowly eroded, their history carried away downstream. Through it all, the earth continued its slow breathing. Subsidence followed uplift. Extension followed compression. The crust never settled into one behavior for long. Patagonia became a landscape of memory, where past structures guided future change. While rivers and basins shaped the surface, another influence worked quietly in the background. Fire. Along the western margin, a magmatic arc continued to supply fresh material to the system. Volcanoes erupted intermittently, sending ash across wide regions. Lava intruded into the crust, cooling slowly beneath the surface. These volcanic materials were carried eastward by rivers. Fresh minerals entered the basins. Volcaniclastic sediments mixed with sand and mud. Poor waters changed chemistry. This had subtle but lasting effects. Bones buried in these sediments encountered mineral-rich fluids early in their burial history. Cementation occurred relatively quickly. Porosity decreased. Microstructures were preserved. Even as the crust deformed above and below, the fossils remained intact. Volcanism also helped build topography. Igneous bodies stiffened parts of the crust. Plateaus formed where lava flows accumulated. These surfaces resisted erosion longer than surrounding sedimentary rocks. Fire, water, and stone became collaborators. None acted alone. Each process shaped the outcome of the others. By the Cenozoic, the Andes were no longer subtle. Crustal shortening intensified. The range thickened and rose higher into the atmosphere. What had once been a low, distant swell became a defining feature of the continent. Subduction beneath South America continued, but not always in the same way. At times, the slab dipped steeply. At other times, it flattened beneath the continent, transmitting stress far inland. These changes altered where deformation occurred and how far it reached. Flat slab episodes helped fragment the fall and even more. Basement uplifts rose far from the mountain front. Drainage systems reorganized again. Later, ridge subduction opened slab windows beneath Patagonia. Hot mantle flowed upward, buoying the surface. Broad regions lifted gently, not through compression alone, but through deep dynamic support. The Andes widened southward. Instead of a narrow spine, Patagonia developed a broad cordillera, cut by valleys, shaped by inherited weaknesses, ready for the next force to arrive. Now, as the story gently loosens its grip, we return, not abruptly, but gradually, to the present shape of the land. The mountains stand tall now. Ice has come and gone. Valleys lie deep and quiet, holding long lakes and slow-moving shadows. Rivers still travel east, carrying the memory of uplift grain by grain toward the sea. The Andes continue to rise, not dramatically, but persistently. The earth has not finished speaking here. Beneath the surface, plates still converge. Stresses still accumulate. Stone still bends, ever so slightly, beneath its own weight. Glaciers have retreated, but their absence is not silence. Steep valley walls continue to shed rock. Landslides murmur into lakes. Sediment continues its endless journey downhill. What feels stable is only slow. Patagonia today is not a completed landscape. It is a pause between motions, a moment where uplift and erosion briefly balance, before the conversation continues. The dinosaurs are long gone, but the basins that once held them still shape the land. Ancient rifts still guide rivers. Old weaknesses still focus ice and water. Deep time never ends. It only changes speed. As this journey comes to rest, imagine the land exhaling. The mountains remain. The valleys remain. The forces beneath them remain as well, patient, unhurried, inevitable. And somewhere far below, stone continues to flow at a pace too slow to notice, yet too powerful to stop. Patagonia is still dreaming, still rising, still wearing away its own edges. And long after this moment passes, long after listening fades into sleep or silence, the earth will continue, layer by layer, breath by breath, becoming something new. Rest here, in the quiet of unfinished mountains, and let deep time carry you gently onward.